Hello friends, welcome to today's operating system class, and in this class we will see the deadlock detection that will come under fourth unit. When come to deadlock detection, there are two types. First one is by using wait for graph we can detect the deadlock, and second one is by using Bankers algorithm we can detect the deadlock in the system. What is deadlock detection? If a system does not have the deadlock prevention algorithm or the deadlock detection algorithm, deadlock avoidance algorithm, then there is a chance for deadlock occurrence in our system. In this situation, we have to implement an algorithm to examine whether the deadlock occurs in the system or not. That is, we need to test the state of the system, whether it is safe state or unsafe state. Safe state or unsafe state. If it is unsafe, then there is a chance for occurring deadlock. Okay, here the algorithm is having two types. The first type, wait for graph. Wait for graph is used if the system resources are having only single instances. That is, all the system resources are having only single instances, then we can use wait for graph. And the next one is Bankers algorithm. If the resources are several instance type, then we can use this Bankers algorithm. Wait for graph. Okay, if all the resources have only single instances, then we can define a variant of the resource allocation graph, which is called as wait for graph. Okay, so what is the purpose of wait for graph? That is used to detect the deadlock in the system. Okay, here we obtain this graph from the resource allocation graph by removing the resource nodes. Okay, and collapsing the appropriate edges. Then we can define this wait for graph. Okay, so this is resource allocation graph. Here we are having process 1, process 2, process 3, process 4 and process 5. 5 processes, and resources see resource 1, resource 2, resource 3 and resource 4 and resource 5. Okay, so 5 processes and 5 resources, and all these resources are connected in this manner. Okay, here when come to P1, the process 1 holds this resource 2, but it is waiting for resource 1. When come to process 2, the process 2 holds R1, that is resource 1, and it is waiting for R3, R4 and R5. When come to R4, it holds, when come to P3, it holds R4, but it is waiting for R5, right? When come to process 4, it holds R5 and waiting for R2, right? But process 5, it's not waiting for any other thing, but it holds this R3. Okay, this is what the situation. Okay, see, sometimes in this particular graph, it is very difficult to detect the deadlock. Okay, hence what we are going to do, we just remove all the resources from this graph, and we merge all the edges, then we will get this wait for graph. Okay, see, here we are having the same 5 process. See, process 1 wanted to complete its process, means it have to wait for process 2 to complete its execution, then only the resource will be given to process 1. Okay, when come to process 2, it have to wait the execution completion of P3, P4 as well as P5, then only the P2 will complete its execution. Right, when come to process 3 have to wait until process 4 have to complete its execution. That is, the process 3 is depending on process 4. And when come to process 4, the process 4 is depending on process 1. Okay, see, process 5 is not depending on any other thing. Okay, likewise, we have to create the wait for graph. See, what is the wait for graph? We have to remove all the resource nodes from the resource allocation graph and collapsing the appropriate edges That means, see, for example, this is process, and process 1, for example, this is waiting for this resource 1, and resource 1 is already allocated to process P2. Okay, see, if P2 completes, then only the P2 will release this resource, and this particular resource will be allocated to P1. Okay, if it is not completed, means what is the indirect meaning? P1 is highly depending on P2. If P2 completes, then only the P1 will start its execution. So this is what the wait for graph. That is simply removing the resource and connecting the edges. Here, a deadlock exists in the system if and only if the wait for graph contains a cycle. Okay, if there is a cycle in wait for graph, then deadlock exists in the system. See, for example, in this particular graph, this is one cycle, here is another one cycle, and here this is another cycle. So many cycles are there. So definitely there is a deadlock in the system. Okay, so to detect deadlock, the system needs to maintain the wait for graph continuously, okay, and periodically invoking an algorithm that searches for cycle in the graph. Okay, so to detect the deadlock, this particular system have to maintain the wait for graph and periodically call this algorithm, that is cycle detection algorithm, to detect the deadlock. The Banker's algorithm, that is, if the resources are having several instances, that is multiple instances, then we cannot use this wait for graph, but the very powerful Banker's algorithm is used to detect the deadlock in the system. See, here we are using the terms available, allocation and request in the Banker's algorithm. First, let us see available. Available is used to indicate the number of available resources of each type. Okay, how many number of resources are there in each type of resources. And next one is allocation, which defines the number of resources of each type currently allocated to each process. Okay, this is allocation. And third one is request. The request indicates current request of each processes. With this information, let us try to write this Banker's algorithm. So first one is initialization step. Here work equal to available, that is available number of resources will be allocated to work for I equal to 0 to n minus 1, that is we are having n number of processes and all the processes initially allocated some resources, right, and the remaining resources are called as available, which are not allocated to the processes. Now, if allocation of I means the corresponding process. If allocation of I not equal to 0, then finish of I equal to false. Okay, if we not yet allocated any of the resource, then what will happen? The process will not finish its execution, then finish equal to automatically false. So initially the finish of all process is false only, everything are false only. This is 0 1 2 3 4, so totally 5 processes are there. Okay, otherwise finish equal to true, that is if we allocate the required resources for this particular process, then this will complete its execution, then the finish will be changed into true, right. Okay, when come to second step, find the index I such that index, here the index indicates the process indicates process index. Okay, both finish of I equal to false and request of I less than or equal to work. Okay, if finish of I equal to false, then request of I. Request of I means the requested resources of this particular process I, that should be less than or equal to work. Work means currently available resources. If it is less, then this particular process I will be executed successfully. Okay, and the allocated resources will be added into the current work, right? Then finish equal to true. Finish of I will be changed to true now. Okay, now these two steps will be repeated until we complete all the process. Okay, and process, that is step 4. If finish of I equal to false, then what will happen? That is some I means process. 0 less than or equal to I less than or equal to 1. Any of the process is not yet finished, that is in false, then the system is in deadlocked state, right? If any of the process is not yet finished, that means if P2 is not yet finished, then the system is deadlock state. Okay, if finish of I equal to false, then Pi is deadlocked. Okay, so by using this algorithm, we can easily detect the deadlock in the system. Now let us see one example for this Banker's algorithm for detecting deadlock. Okay, consider a system with 5 processes P0 to P4, that is P0, P1, P2, P3 and P4, and 3 resource type A, B, C. Okay, the resources are A, B and C. Okay. The resource type A has 7 instances. A has 7 instances and B has 2 instances. B equal to 2, and resource type C has 6 instances. This is equal to 6 instances. Suppose that at time 0 we have the following resource allocation state of all the processes. Okay. See, this is the allocation, this is the request and this is available. Okay. See, we are having 7 instances from A. Okay. So 7 instances, 2 plus 2 equal to 4 plus 3 equal to 7. Okay. When come to B, B only 2 instances are there. Okay. When come to C, C is having 6 instances. So totally 6. Okay, then what is the available? All the resources are allocated to the processes, hence available equal to 0, right? And this is the requested resources to complete its execution. So further requirement will be given in this place. And now let us try to solve this particular problem. The first step is initialization step, that is work equal to available and finish of I equal to false for I equal to 0, 1, etc. up to n minus 1. See, I indicates the process. Here we are having 5 process P0 to P4, that is this is P0, P1, P2, P3, P4 and all are not yet finished, that is finish of I equal to false. Currently everything are false. And first let us take this first process P0. Okay, P0 work equal to available. What is the available resource? We are having 0. Okay, so that 0 of A, B, C everything will be allocated to this work. Now request less than or equal to work. We need to check whether request of this P0 is less than or equal to work. What is the request of P0? That is 0, isn't it? 0 is equal to 0. Hence, no problem. This is true only. Now, the work equal to work plus allocation. What is the allocated resources for P0? Which is equal to 0, 1, 0. That is A type 0, B type 1 and C type 0. Okay. So, that will be now the work. Okay, the current work is 0 plus, that is 0 0 0 plus 0 1 0, which is equal to 0 1 0. This is the current work, right? First P1 not got finished, so this is finished. And now we will take this P1. Okay, work equal to available. So what is the current available resource? 0 1 0. And request less than or equal to work, we need to test. we need to test whether the request is less than or equal to work. What is the request of P2? 2, 0, 2, isn't it? So this is what the request. But this is greater than the available resources 0, 1, 0. Okay. So this is not true. Hence this is false. So P1 have to wait. P1 now have to wait. Okay. So this is P0, P1, P2, P3, P4, P1 got finished, P2 have to wait now. Now let us take this P2. Okay, process 2 is here. Current available resources are 0, 1, 0. Now what is the request of P2? The request of P2 is 0 only. Okay, request is 0. What is the current available resource? 0, 1, 0. So this is of course less than or equal to the work. Hence this is true. The condition is true. Hence we can easily allocate resources for this P2. After executing this, the P2 will release these resources. Hence, this will be now added into work. Okay, what is the current work? 0, 1, 0 plus the allocated resources for P2 is 3, 0, 3. What is the result? Result is 3, 1, 3. That is 0 plus 3 equal to 3. 0 plus 1 equal to 1, 0 plus 3 which is equal to 3, right? Okay. Now P2 got completed and it will change into true. Now let us take this P3. P3, the current work is 3, 1, 3 and this is less than the request. What is the request of P3? Request is 1, 0, 0, isn't it? So the condition is true. Hence P2 will execute successfully. After executing, that will release this particular resources. Okay, see, now that will be added into current work. 3, 1, 3 will be added into 2, 1, 1, which is equal to 2 plus 3 which is equal to 5, 1 plus 1 equal to 2, 1 plus 3 which is equal to 4. Okay. So P3 also executed successfully. And now this is P0, P1, P2, P3 and this is P4. Okay, now let us take this P4. What is the current available? 5, 2, 4. Okay, the request of P4 is 0, 0, 2. That is of course less than the current available resources, hence the condition is true. Okay, hence P4 will execute successfully without any shortage. Okay, now after executing, the P4 will release these resources. Okay, that will be added into currently available resources. Okay, that is 5, 2, 4 that will be added into 0, 0, 2. Next, what is the result? 5, 2, 6, isn't it? Okay, now we will come back to this first process, that is P1. Okay, so this is got finished, this is also finished, this is finished and this is also finished. Only one is pending for us. Okay, now what is the current work? This is our current work, that is the available resources 5, 2, 6. Now request is less than or equal to work. We need to test. What is the request of P1? Request of P1 is 2, 0, 2, isn't it? So 2, 0, 2 is of course less than 5, 2, 6. So the condition is true. Hence the P1 can execute its process successfully and it will release these resources. Okay, once it completes, then that will release. Okay, the currently released resources are 2, 0, 0, that will be added into the work. Okay, now we will get the final resources. After completing all those process, then we will get our original resource, right? And finally we have to write the result, that is in what sequence we have to execute the process if it should not get any deadlock. Okay, that is the finish of I equal to true for all I equal to 0, 1, etc. n minus 1, right? See, first we have to execute P0, then P2, P3, P4, after that P1. If we execute in this sequence, then there will not be any deadlock in this system. So this is what our result. Up to this we have seen the deadlock detection algorithm. There are two types. First one is single instance of each resource type. For this we have used this wait for graph, and second one is several instances of a resource type. Okay, for this we used this Bankers algorithm, and we have seen one example for this Bankers algorithm also, right? So in the next class we will see another important topic from 4th unit. Thank you.